Hello everyone, I'm Winson and I'll be presenting on my FYP project EEG-based mental state recognition for arousal self-regulation system. This project is centered around the use of brain-computer interface system, also known as BCI. BCI allows communication with computer system through the use of brain signal and can be used to perform actions or even play games. Some standard component of a BCI-based system includes a headband with EEG sensors and a model that classifies the mental state that the user is in based on the EEG signal. The output of the model can then be used by different systems or programs to perform their respective tasks. But to first use the BCI device, it needs to be calibrated according to the user's EEG signal. Different users will have different EEG signal, and although they may be performing the same task and in the same mental states, the model might not classify them correctly due to differences in EEG signal. The focus of this project is on arousal management, which comprises of a variety of emotions. But the main emotion that I'm looking to tackle is anxiety and stress. Current arousal calibration works by introducing an arousal-inducing task and an arousal-reducing task. The subject will first be exposed to an arousal-inducing task, and the EEG signal collected will be labeled according to the state and fitted into the model. The process is then repeated for the arousal-reducing task. The calibrated model will then be used in an arousal management program, where the user will first be taught arousal management techniques such as mindfulness practices or breathing exercise. They will then be exposed to arousal-inducing stimuli or tasks, which they will then attempt to cope with the arousal level through the technique learned. The issue identified in the arousal management program is that the system is only able to classify arousal states. In instances where the arousal level is not showing any improvement during arousal management, there is no way to identify the possible reason. An improvement could be made through incorporating more mental states into a calibration to get a better picture of the overall mental state of the user. The other mental states includes attention, working memory, and affect states, which we will be incorporating into our baseline. Another issue identified is that most calibration use the same stimuli to elicit arousal state across all subjects, but using a common set of stimuli may not be effective to all subjects, as there will be personal likes and dislikes. To attempt to improve arousal elicitation, I'll be using personalized stimuli in this experiment. The personalization will be done through an online survey that the subject will fill up prior to the calibration, which aims to understand their likes and dislikes better. After the calibration is completed, the model will be incorporated into a virtual reality arousal management training system to provide neurofeedback for guiding the user. The calibration task can be split into baseline calibration task and the arousal calibration task. The baseline task consists of attention, working memory, and affect tasks, while the arousal calibration consists of arousal game, arousal video, deep breathing, and body scanning tasks. The attention calibration will use flanker tasks to elicit attention, where the subject have to respond to a series of patterns according to the congruency. For the inattention task, audio-visual white noise will be played to elicit inattention. The subject will first perform 15 seconds of the attention task, followed by 15 seconds of the inattention task, which will make up one cycle. There will be a total of 10 cycles the subject needs to perform. The working memory task will use n-back tasks that require subject to remember different number of fruits based on the level of working memory that is to be elicited. For high working memory, subject will need to remember the last 3 fruits shown and respond when the fruit shown 3 sequences ago is the same as the current fruit. For low working memory, subject just need to remember the previous fruit shown. Each working memory task will last for a duration of 2.5 minutes. In the affect task, subject will be shown personalized image based on their likes, dislikes, and neutral rating to elicit positive, negative, or neutral emotions. There will be a total of 150 image shown, comprising of 60 images of positive emotions, 60 images of negative emotions, and 30 images of neutral emotions. In arousal calibration, subject will perform 2 sets of tasks comprising of 1 arousal-inducing task and 1 arousal-reducing task. In one set of arousal calibration tasks, a fruit slicing game is used to elicit arousal, while a deep breathing exercise is used to reduce arousal. In another set of tasks, a video which consists of personalized clips is used to elicit arousal, while body scanning is used to reduce arousal. The model is trained using deeper deception deep learning algorithm using leave one subject out cross-validation method at a 95% overlap. The result produced for each model is as shown, with reasonable accuracy achieved for the attention and working memory tasks. For the arousal task, good accuracy is achieved for the combination of arousal game and body scanning tasks. The model created will next be incorporated into arousal management training system. The system will first induce arousal through a gameplay of catching pigeons, and after a certain threshold of arousal is met, the user will be introduced to arousal management techniques. The management techniques includes visual imagery, deep breathing, and breath counting. While the user performs the task, their arousal level will be monitored, and through the use of neurofeedback, their VR environment will change incrementally to let them know that they are making progress. The subject will start off with a VR environment that is filled with fog and rain, and as they progresses, the rain and fog will clear up to reveal a beautiful scene. There will also be spheres in the center of the forest that will incrementally turn from grey to blue to provide quantifiable feedback to the user. And with this, I have reached the end of my presentation. Thank you.